Any questions about lecture on Friday? New material, including the 2 videos. Question?
For the reactive flow that you were saying, by breaking the fluorine bond and making the carbon-fluorine bond, are we going into less entities and the carbon-fluorine bond has more energy in one state?
I don't think it has more energy. More energy is not more stable. More energy is less stable. Okay, guys. See where we left off at. Reaction coordinate diagram for the reaction above. Let's draw it again real quickly. We have reaction progress. Some type of energy. We had A, B, and C, right? A. C was more stable. Lower in energy, we made 2 sigma bonds. We had a higher energy intermediate, B. Something like this. This was the carbocation intermediate. We went something like, still we can draw this a little higher. Like this, energy well, and then we have a transition state leading to the final alkyl halide. Falling downhill, not much transition state energy needed to fall downhill. Rate determining step is the first step. Let's look at the reaction down here. Same starting material, alkene. What is this, 2-methylpropene? That seem right, 2-methylpropene? Reacting with HBr. Major product is shown above. Not this product. The product above, the bromine ends up on the tertiary carbon. We can add HBr across the pi bond a different way. We can put the bromine on this carbon and the H here. There's a new H here, right? Got to know where your new H's are. This reaction does not occur this way significantly. This is not the major product. And anytime we are looking to give a product, we're looking to give the so-called major product. A reaction may give other products. But typically we're going to always ask, what is the major product for this reaction? The major product is shown above. The bromine is on the tertiary carbon. Not this product with the bromine on the primary carbon. Maybe this is formed in a 5%, 10% amount. But it's not the major product. We thus say the reaction is regioselective. The bromine ends up on one region, the tertiary carbon, and not the other region, the primary carbon. Again, site-selective may be a better term, but we call it regioselective. Why is this reaction regioselective? Why does it not give this? Well, if it gave this, where's the new H? The new H is here, right? The H comes from the H of the HBr, and it's H plus Br minus. We can show it ionic here if we like. That's okay. Pi electrons, to get to this product, we have to pull the electrons this way with the bond to the H here. It's like a hinge, it's like a door. The electrons are pulled open this way. If we want the bond, carbon H bond, pull it this way. And this bonds to the H. That will give boom, 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 bond to the H, leaving this as a carbocation because it only has two H's there. Only 3 bonds. Then the next step to get that product would have to be Br minus. We don't have to redraw, it's right here. These electrons then bond here. And that would be a mechanism for that minor product. Why is it a minor product though? Well, we can put the reaction coordinate diagram on the same place. This is A. Same as that A. We can call this something else, X. It's not the same as C. I reckon I can call this something else because this is not the same as B. That's very important. Look at B. What type of carbocation is B? The cation is on what type of carbon? Tertiary. Tertiary. B there is a tertiary carbocation. What type of carbocation would you have to have if this was the reaction pathway? Primary. Tertiary is better. Why? Inductive effects. How do you stabilize a cation? Do you push electrons towards it or pull electrons away? You stabilize a cation by pushing electrons towards it. Everything wants to be more towards neutral. Well, this guy has 3 rich friends. sp3 carbons inductively donate. That's going to stabilize that poor carbocation. Electron poor. The carbocation we made down there is only primary. It's only got 1 rich friend. If you were poor in terms of electrons or money, would you rather have 1 rich friend or 3 rich friends? 3 is better. That's a more stable cation. You've got to know when you look at molecules, there's fluidity here. You have to know polarity, induction, resonance. Electrons aren't just sitting there like we draw it on the board, right? Tertiary is better. Since it's better, what do you want to call this? Well, how about the next letter? I used X there, A, B, C. How about D for this one? Where do you want to put D compared to B? Yes, it's higher. It's not as stable, it's primary. All right? And so here's the reaction. This can react with HBr 2 different ways. If it reacted to give B, we already drew that pathway. If it reacted to give D, what would that look like? It would look like that. Which is going to be formed preferentially, D or B?
D.
B. Not going to be formed. B. And since B is formed, which product do we get? C, because C only comes from B. We only get X if you first make D. This should hopefully explain why you don't get much of product C. Can you get any? You might say, well, why do you get any? Well, I mean, sometimes there's enough energy to push it up the hill. Hurricane. Water comes running down the road. You got 2 forks. One's like this and one's like this. Is the water going to go downhill or up? It's going to go down. Could any go up? In a hurricane, you're probably going to get some going up as well. Well, if there's lots of energy here, you might get some going D as well. But guess what? The B pathway is preferred. The major product is C, not X. We predict C to be the major product. The reaction is regioselective. The bromine is preferentially going to end up on this region, not that region. Again, anytime I say region, you can substitute site. That sounds like a better word, but guess what? We use region. I didn't make that term up. Site selective, regioselective, not here. Bromine's going to be here. All dictated on what cation is going to be formed. Would you rather form tertiary cation or primary? Tertiary. There's your pathway up there. Not this way. Cation stability. Tertiary is better than secondary, that's better than primary, and that's better than methyl. A methyl carbocation is not even primary because it doesn't even have one rich friend. But other things can affect carbocation stability. For example, resonance. Resonance can affect carbocation stability. There was no resonance in the example we looked at. Effect on the reaction coordinate diagram, well, we looked at that. Okay, let's see how we did on these over here. Major product of these reactions. Looks like we have alkenes reacting with HX. This looks like a hydrohalogenation reaction. Anybody have product for the first one? Got something for the first one? Good. Anybody else? You drew in your H. I reckon that's okay, but I mean, it strictly is okay.
For the last one, would the iodine bind and just go to the center for because of the induction instead of speeding towards the end?
No, there's not going to be any regioselectivity there.
Okay.
Two different cations. Which one's going to be preferred?
Well, they're the same cation, but their location inside the molecule is different. I was thinking that.
Yeah, and I don't. There should be a slight difference, but for what we presented, no difference. They're both secondary. And we're not going to be able to distinguish, and so we wouldn't expect any selectivity. Now that's the opening comment. Deeper analysis may give you a reason to go one or the other, but for what we're doing, no. Okay, again, guys, these should have been worked before class, right? All right. I bet you're going to stop telling you this. We're going to eventually just plow ahead, and all right, we're already a third through the course. All right. The expectation is that you've looked ahead, you've worked problems, and you're ready to go. Yeah. Okay. Reaction here, we have H plus, Cl minus. We can again show that covalently or ionically. The question here really is this: where are we going to make cation? That's what we asked on the previous example. All right. Where are we going to make cation on the previous one? Left or right? Where do we make cation at?
Left.
Left. That's going to be a tertiary site. Okay. Where are you going to make cation here? Top or bottom? Top. So the electrons, here's the pi bond. Pull it down away from the top and go make bond to H. Pull the electrons down from the top, go make bond to H. These electrons are pulled down and go make bond to H. Okay, we'll do this mechanistically. We don't have to just memorize an outcome. We have a thought process. Mu H here, some methyl here. What do we show at the top then? Carbocation, because that carbon only has 3 bonds. Is there an H there? No, there's no H here. How many H's here? 1. How many H's here now? 2. I only drew 1 in. By the way, my rings may never really attach. That's a 6-membered ring, right? That's a carbon there. Yeah, you good? Okay, we made a tertiary carbocation intermediate. All these reactions we're doing have carbocation intermediates. That's what it said in the heading on the previous page. What then attacks carbocation? Chlorine. This nucleophile, these electrons attack here, and we get final product. Methyl and the chlorine. Chlorine ends up on this carbon, not that carbon. And so we added HCl across the pi bond, chlorine here, H here. We do expect that to be regioselective. You would never do this the other way and put cation here. That would be secondary. Tertiary is preferred. Product here, where do you want to make cation? Left or right? Correct. These electrons attack H+. Okay. All right. What do you think about that arrow right there? What does that arrow mean? I don't know what that arrow means. That arrow is nonsense. I couldn't begin to explain what that arrow means. It means nothing. These electrons, what electrons? None of the electrons over here are doing anything in this reaction that we're going to show. But these electrons we're going to pull away from this carbon and go make bond like a hinge. So we take these electrons and pull them away from that carbon. All right? And that's going to give boom, boom, boom. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. New H here. Carbocation here. Right? Here, somebody pull them up in. Take it. You're going to pull it away from this carbon because that's where you want to leave a cation with it lost the bond. Pull it over there. That's what the arrow just did. And now this carbon is bonded to the H like that. You got to have precise meaning of your arrows. Mainly because you have to have precise meaning in your head of what you're doing. And if you can't show a precise arrow, then that means to me that you don't know precisely what you're doing. Or would you rather pull it this way and leave cation on the right? No, that would be a primary cation. We made a secondary cation. Next step is these electrons then make bond, and there you go. You get iodine here. What's that? 2-iodopentane. Both of these should be regioselective. Where do you want to make cation here, right or left? If you made it on the right, it would be secondary. If you made it on the left, it would also be secondary. Which is better, secondary, secondary? As we were talking, we have no reason to say one's going to be better compared to the other. In this case, later on, maybe we got two secondaries and one has resonance and one does not. Well, then that would be a reason. Anytime I erase with my left hand, I'm reminded of how they do it in med school and graduate school and everywhere. They write like this. Okay? Keep the board clean. All right? Because the cations down here will be either there. So redrawing the structure, I'll draw it the same thing. Would you rather have cation here or here? I mean, they're both secondary, so there's no difference for us, and there's no resonance. You get both. So I'm going to draw it down here. We could get product with iodine here. We also would get product with iodine there. cation in either place is just as good, and so there's no reason for us to suggest that there's going to be any regioselectivity here. The top two reactions you are going to be able to do and get a good yield of the products we showed. This being the major regioisomer. Third reaction, you're going to get both regioisomers in major. It's going to be almost 50-50. It's not going to be easy to purify. No regioselectivity.
Here, Stephen. Why do you drop off your H?
Because when we draw line bonds, we typically don't draw H's.
Okay, so just when we're going through the process, we can add on the H, but with our products, no H's.
Well, you say, you can do however you like,
Okay.
whatever works for you best. Okay? As I said on Friday, I will typically show the H we just added, but I will not move as we continue forward. All right? Synthesis. Synthesis is where you go backwards and you're thinking backwards. Looking at a product, how would you make it? Typically, you're going to be asked to propose a synthesis. And the synthesis you propose, it needs to be high yielding, expected to be high yielding, expected to be regioselective. How would you make this compound here?
For it to be regioselective, the double bond has to be between the 1,2 carbon, right?
Yes. Now when I say how you make this compound here, you only know one reaction so far, reacting an alkene with HX. So hopefully that's the answer, at least for you to start thinking of. Now down the road, you may know more than one reaction. You may know 10 or 20. Okay? And so you're going to have to keep your reactions sort of cataloged. What reactions do you know? This becomes what I call your toolbox. Okay, right now you only have a screwdriver in your toolbox. So if I ask you to use one of your tools, it's going to be a screwdriver. But once you get a more complete toolbox, you're going to have to decide which tool you want to use. All right? Yes, we can back this up. When you go backwards, a double-lined arrow like this. I'm going back to a precursor. It can be either, it's going to be an alkene again, because that's the only reaction we know. So that's alkene, boom, boom, boom. So we can draw that alkene, or we can draw that alkene. Which alkene would you propose to start with? If we want a high yielding.
One on top.
One on top. Because when this react, now going forward, we show this with just a regular arrow, and we would react this with HBr. Where are you going to make cation? Left or right? Right. Secondary carbon, then the bromide attacks it, and you'll get that product in a high yield. Here, where are you going to make cation? Left or right? Either. If you make it here, you get that product when bromine attacks. But you can also have the reverse regiochemistry, just as well. It's going to be a more predominant mixture of the two possible regioisomers. Okay? Yes, that could theoretically give this product if this reacts and puts the H here and leaves a cation here. But no, this is not regioselective. So we would propose this route. Again, this is called a retrosynthetic or retrosynthesis error, where you're going backwards. I would make this from this. This is my thought process. I'm going back to what I could start with. Then I can show coming forward. How about the one on the right? Can you show how you would make that compound? go back to, again, an alkene. What alkene, though? How about that alkene there? If we react that alkene with HCl, would it give that product? In a high-yield regioselective. Where are you going to make cation? Left or right? Left. It would be tertiary. Can you envision this mechanism? Alkene attacks H plus to give cation. And then chloride, Cl minus, attacks cation. Yes. Question?
Does it matter what side the double bond is on?
You want to show that there?
Mm-hmm.
Okay. Is that a different answer? I can't hear you.
It's a stereoisomer, isn't it? 'Cause it's American.
That's the stereoisomer? Now, what's the name of the compound on the left? You should be able to name that compound. I could have put that on test 1 right there. 1-methylcyclohexene, right? Well, no, that's an alkene. It'd be on test 2. You watch nomenclature video? It's just, instead of cyclohexane, it's cyclohexene, and you got a methyl at the 1 position. 1-methylcyclohexene, what's the name of the other? Same name, it's the same compound. I mean, if you showed it 2 different ways, you'd be just showing it twice. Same compound, right? Those are the same compounds, yeah? Not stereoisomers. You need to make sure you see that. Okay? So is that it, or is there any other possibility?
The alkene could be in the place of the methyl.
What if we make the alkene up like that? You can do that. It's just a carbon-carbon double bond. Got a carbon up here to make the pi bond there. Now that's not the same as that. I don't know. I don't think we're going to be able to name this guy because it's, yeah, we can react this with HCl. Will that work out? Would that be a good? You're going to make cation on top or bottom? Bottom. Hey, by the way, both of these reactions here are both regioselective. They both give the same carbocation intermediate. Both of these have the same carbocation intermediate, yeah? Same intermediate. Should I see that?
New H would be in a different place. Is that all?
Do what?
It's just that the new H would be in a different place.
Correct. But
It'd be the same, but it just...
Yeah, but H is an H. Yeah, I mean, H plus, these electrons, what we're going to do? Are you going to pull the electrons away from the top or bottom?
Away from the bottom. Away from the bottom.
Away from the bottom, yes. Pull them away from the bottom, they're going to hinge. Here we go. Pull them up in. You're not going to pull from up here. No, you pull from here. You go up and you cation here, new bond to H up there. There's a new H up here. Because now there's 3 up here. Where there was only 2. Same thing here. There's 2 H's here. Where there's only 1. Either way there is good. Either way is regioselective. Either way is going to be good. Over here, though, there was only one way that was good. One to do below, think about this one. Think about this one. Okay, next reaction. And again, green is two different places we're at. We just looked at reaction of the HX to give alkyl halides, yeah? Now we're going to look at reaction with water, but we've got to have an H plus catalyst. And we're also A2. So you know where we're at with the outline. This is going to be called hydration of alkenes. Hydration meaning with adding water. Okay, this reaction gives alcohol. Now, an alkene does not react with pure water, no reaction. The skin of an apple is largely various alkenes. Those alkenes serve to protect the inside of the apple from the rain. Alkenes don't react with water, or when it rains, you have a problem with the skin of the apple. Okay. Now, acid rain is different. Problems with acid rain, because acid rain brings in the H+. An alkene will react with water if you have an H+ catalyst. Okay? Now, of course, if you show water and H+, it's often shown as H3O+. Acidic water. Alkene reacting with water. Remember, we're doing addition reactions. This formula is this. This formula now has H2O added to it. And you can see it in the structure as well. The structure has H2O added. There's an OH, but that's not H2O. Where's the other H? Well, it's right there on the end, because there's 3 on the end, where here there was only 2 on the end. So the pi bond used to be here, but we added water across the pi bond, H2O. What type of H+ catalyst is most common? These here, sulfuric acid, phosphoric acid, or HF. Those are 3 common strong acids. Now, they may not be the strong ones you call them gen chemist strong, but they're strong enough to be an H+ catalyst here. You do not want to use HX like HBr or HCl, because if you do, you'll get the previous reaction out to them. The reason these work is because the conjugate base here will never do anything in this class, including F-. F- will not attack the carbocation, but Br- and Cl- and I- will. Previous reaction. We'll mention that again when we look at the mechanism. Mechanism. And when we do mechanisms, you need to look for the consistencies. Okay? Alkene. This can be shown in a variety of ways. This is aqueous. That means water, right? Water and acid. Acid, H+. Alkene doesn't react with water, so you don't want to show that as a starting point. It doesn't react. But it will react with H+, just like in the previous reaction. H+ comes from the acid. You can show that ionized already. H+. Where are we going to leave cation? Left or right? Left. Correct, on the left. So these electrons go attack the H. New bond here. Sometimes I will highlight the new bond with a squiggly line. We just made that bond. Here we go. Alkene, ICNH+. I'm going to break away from U carbon and go bond to that, leaving U as a plus. New bond to H. Carbocation intermediate. Electrons can now attack the carbocation. What is going to be the nucleophile? We have water. We also have HSO4 minus. We can draw that out. Like I just said though, the conjugate bases of these acids will never do anything. Never do anything with that in this class. It's too weak of a nucleophile. And for various other reasons. Okay? So what can attack the carbocation? Water can, and that's the only thing here. These electrons make bond to carbocation. We get this here. What bond did we just make? Right here. Oxygen lone pair bonded to carbocation. And guys, you got to look at what you're doing here. For example, I almost all the time will see something that looks like this. Water just bonded here. Really? What does this mean? Are you saying the H is here? I mean, is the oxygen bonded to this carbon? This is just not sufficient. You just show bonds. Okay? I mean, is the oxygen charged here? It's no good. We have the bond shown here. And yes, the oxygen is charged because the oxygen has 3 bonds. And as we said on day 1, if it ain't a standard oxygen, it's going to be charged. So you need to be able to determine your charge and show a good structure. What does the arrow mean? The lone pair just made a bond to the carbon. And that's what we have here. Okay. This is not our final product. We need to lose one of these H's. All right, this is where we need to get more precise. This is really not good enough. What's going to take the H? Something's going to take it. We can use the conjugate base to take the H. This needs to be drawn out better. Lone pairs where the charge is. That should be sufficient. You don't really need lone pairs over there for me. Anytime you have a charge, you want to be very complete about it. All right? These electrons can take the H. This is just an acid-base reaction. This acts as a base, makes bond to the H. These electrons move on to oxygen. What does that do? Well, now we have final product because now we get the lone pair back and we have 2 lone pairs. That's final product. But what do we reform here? We reform our catalyst, H2SO4. And that's why it's called a catalyst, because it's reformed. What did it do? It initiated the reaction. It supplied the H+, because otherwise there's going to be no reaction. Now you can say it lowered the transition state. Yeah, it lowered it enough for there to be a reaction. Because if there was no H+, the transition state is so high that it's not going to happen. And there we go. You could also use water to take the H. Because this is aqueous. And how does sulfuric acid exist in aqueous environment? It actually exists like H3O+. We could use water to take it. That's actually strictly more correct. If we use water to take the H, what do we form? H3O+. And again, that's how sulfuric acid exists anyway, right? I like to reuse the conjugate base so I can reform the actual molecule of the acid. I think it's cleaner for us that way. But as you learned in Gen Chem, H2SO4 exists ionized in water, right? Right. How many intermediates in this reaction? Actually two, the carbocation and then the oxygen cation. And so if you did a reaction coordinate diagram here, you'd have two intermediates. Do you see the similarities in previous mechanism? Really the main difference is we had to take care of the proton. And taking care of a proton will be in many of the mechanisms we do in organic 1 and organic 2.
How do we know when to use which mechanism? Between the hydration of alkenes and then the other one with the HX?
Well, if you're using HX, you do that mechanism.
Well, will the question tell us, okay, will it say use HX or use water? Or will we just be given alkene and then?
You have to be given something. I mean,
Okay, what will we be given? Can you tell us?
well, there's plenty of examples all throughout.
Okay.
Yeah, I mean, we haven't did a predictive product yet. Well, we did. We did some over on the page, and there was 3. We predict products.
We only had one tool in our toolbox at that point, though.
Right, I explained that.
So now we have 2. So now I'm just curious as to
Now we're doing hydration. How do you hydrate an alkene?
water.
Right, water, not HX.
Okay, so it'll say hydration.
No, you know that.
Okay.
How do you hydrohalogenate an alkene?
With HF,
Okay, how do you hydrate an alkene?
with water.
So you know it, right?
Yes.
You don't hydrate an alkene with HBr. You agree?
I agree. I was just curious as to how the question would be formatted.
We'll get there.
Okay.
Keep at it. Okay. There's some things below, including some. Okay. 2 types of reactions we'll generally see. One is predict products. I'll give you a line reaction and ask you what's the product. The other type of question you'll see here is mechanism. Okay? I'll give you, like up there we did mechanism. Up there I didn't ask you what the product is. I gave you the product. And I said, okay, show the mechanism. Now, that doesn't mean that down here you don't need to show the mechanism. Well, you don't need to show it for any credit. But down here, I highly, highly, highly suggest that you do this mechanistically. Okay, your mechanism is like your formula in math. You use your formulas to get your answers, right? Where you use your mechanism here to predict your product, and your mechanism is just going to be on your scratch paper. And I'll never grade the mechanism here, but you use it to get the product. All right? But on another question, I may actually grade your mechanism. All right? So, predict products here. And we need to talk about stereochemistry. But basically, again, guys, you need to be looking ahead. All right? All right? I think we're done, yeah? Good? Yeah? What are we missing? I think we're good. Have a good day, guys.